Good evening, everyone. Welcome to session 6 on the OFDM dilemma and potential new waveforms for 6G of TSDSI Tech Deep Dive Conference 2025. I am Vaishali Upperwal, coordinator of this session. Convener of this session is Mr. A.K. Mittal. Shri A.K. Mittal currently serves as the Director General of the Telecommunications Standards Development Society India, that is TSDSI. He is also associated with TSDSI as advisor with special focus on standardization in wireless and wireline systems and handles standards related activities of TSDSI in 3GPP and ITUR. Before we proceed further, I'll go over a few hygiene instructions. This session is being conducted in online mode over AirMate tool, guidelines for online participants. All online attendees will be kept on mute throughout the session by default. Kindly post your questions in the Q&A tab of the conference tool. These will be taken up during in the Q&A section. Questions in the chat box will not be entertained. If you want to enlarge the presentation, please click on the expanding arrow icon at the top right of the presentation screen. The tool is configured for HD video. You may switch to LD in case you are facing bandwidth issues. Attendees may like to visit the exhibit booth of TSDSI in between the sessions to know more about our work. Attendees can use the launch facility for networking. The launch will remain open till the end of the conference. The conference sessions are being recorded and will be posted to the TTD website in the next few days. Now, I would like to introduce the co-chairs of this session. The co-chairs are Mr. Prakash R. and Mr. Pradeep Hirisave. Mr. Prakash R holds the designation of Scientist G in CDOT. He has been working as a researcher in the telecom industry for the past 30 years. His current interests include software-intensive telecom systems, wireless networks, that is 4G, 5G, 6G, data networks, cloud computing, software-defined networks, open source, and standardization. He is an IEEE senior member, ITE fellow, and ACM member, and also serves as chair in the study group networks of TSDSI. Mr. Pradeep Hirisave, AVP, Products and Telecom Standards at Reliance Jio, has over 19 years of experience in wireless communication. He focuses on 5G and beyond standardization through TSDSI, 3GPP, and GSMA. He holds 40 plus granted patents and has contributed to IoT or IIoT projects such as smart agriculture, smart cities, and smart electricity meters. Now, I would like to hand over to Mr. Prakash R for opening remarks and further proceedings. Over to you, sir.
Okay, thank you, Shweta. I'm audible.
Yes, sir, you are audible.
Okay. So welcome everyone. Thanks for being here, and thanks to all the distinguished speakers for joining us on this session. I also thank TSJSI for making me and Pradeep the co-chair so that we could coordinate and support this activity. So, just a brief on the session. Okay, so the session is titled The OFDM Dilemma and the Potential New Waveforms for 6G. So, waveforms are used to encode information, okay, and in communication, and it's a critical and integral part of the communication system. So, we could almost say that it's a cornerstone of wireless communication system. And there is a lot of research and development that goes across the world, but it's a specialized field. And the reason is the waveform design and engineering, it requires to meet a variety of criteria, the data rates, redundancy, reliability, interference, encoding, latency. Okay. And typically very advanced waveform techniques are used in our modern communication systems. And OFDM has been what OFDM, if we expand, it's the orthogonal frequency division multiplexing. It has been a workhorse waveform. You can say it is the one of the most predominant waveforms. It's been used in a variety of technologies. Mostly it's the LTE or the 4G and 5G along with Wi-Fi. Okay. While OFDM, while it has a waveform, while it has its strengths, it also has a set of issues and criticism, which I will not talk now. I'll let the speakers spend time elaborate about it. But as we go for past few years, 4G, 5G has been very widely deployed. Past 10 years, 5G has been deployed in the past 3 to 4 years, which is predominantly OFDM, and the 6G research has started. A lot of people have started doing work on 6G. R&D is got started. The focus of 6G is to improve upon data rate, improve coverage, improve connectivity, improve energy efficiency. While there are a lot of other goals from the technology and engineering perspective, the new changes or the scenarios or the dimensions that are coming in are ability to integrate satellite, the broadcasting, and try to fit into new use cases like robotics, drones, sensing, and positioning. Okay. And in this context is where 6G waveform design is getting a lot of focus. And one of the constraints that has come is that it has to be, of course, better than OFDM in parameters, and it has to scale up to meet the 6G. Okay, a lot of people are researching. We now have presentations on the from top experts. We will then have panel discussion. We again have about 7 experts. We will debate. We'll discuss the waveform, what is the weakness, what is the roadmap, and what are the standardization. So given this context, I will now hand it over to my co-chair, Pradeep Irisave from Geo. He will introduce the speakers, the initial 3 speakers, and the whole section he will handle the speaker. I'll get back on the panel again. Over to you, Pradeep.
Okay. Hi, I think I'm audible.
Yes, go ahead.
Thank you, Prakash. Thanks for setting the overall context of the this particular session. And this is as we see on the screen, we have around 3 keynote speakers. So we have first keynote from Mr. Meg Kotkamp. He's from R&S, and we have one presentation from Dr. Radhakrishna Ganti, and one more by Mr. Satish Jamadagni from Reliance Jio. So if you can go to the next slide, I would like to briefly introduce Mr. Meg. Yeah. So Ms. Meg Kotkamp, so welcome to session on OFDM dilemma, and our gratitude for you to accepting and sharing your views in this session. So about Mr. Kotkamp has almost around 30 years of technology experience, and in the cellular industry, he's a principal technology manager in RNS. He's based out of Munich, Germany. He's also responsible for strategic marketing and product portfolio development, primarily focusing on 5G NR, and again in that specifically on the industrial applications, going forward on 6G also. Mike was with R&S from August 2007, and also after and before R&S, he was with Siemens and NSN for almost 11 years. So he's a very senior veteran in this domain. I would welcome Mr. Meg to please take over and share his opinion, and you can start your presentation. Mr. Meg, you are available, and can we present the slides on the topic from Mr. Meg? So basically, he'll be talking on OFDM or no OFDM waveforms for 6G from TNM perspectives.
Yes, hello and welcome also from my side. Very much appreciate the invitation and the possibility to speak at this conference. I had the chance to listen in the one or the other session before, and I found this a very valuable conference already the last 2 days. So I like to present myself, but I cannot really hit the presentation button. Now I can. Thank you very much. So let me bring up my presentation. Let us get started. So again, welcome from my end. So I like to start off with a very shortly introduction of our company, because I'm not sure how many people do know so much about Rohde & Schwarz. So we are here in Munich, in Germany, headquartered. Quite old company. The two gentlemen on the left-hand side, you can see here, are the founders of our companies. It happened more than 90 years ago. Meanwhile, of course, we are quite global, so locations in around 70 countries, about 14,400 people working at Rohde & Schwarz. You potentially know us mostly from the test and measurement division. That's also where I am coming from. That's also the reason why the title of the presentation, when we discuss the waveforms, are a T&M perspective in that. You should know there are also other two areas or in our company, which are technology systems for secure communication. It's also spectrum monitoring solutions, also this bigger white blocks. These are TV transmitters we do build. And there's also an area on networks and cybersecurity, which is a smaller one, but also part of the company. So this should serve just as an introduction. And then moving forward to our subject today, obviously there is a time frame that maybe if you have listened to earlier sessions during this conference, you have been seeing. We have now a clear way forward in 3GPP, where we will start now. Actually, we have started now and will be more concrete in the release 26G studies ongoing in the various working groups. That will be followed by the normative work that we expect to take place in release 21, around 2027-28 timeframe. And then obviously we are all working towards a commercial deployment of first networks in the 2030 timeframe. Along that, we have the discussions on spectrum, which is also kind of a related discussion to waveform in my view. So you can see here that we have initial spectrum discussions as early as at the November World Radio Conference in Dubai, where some study item bands were identified, as you can see here. And then there is the next World Radio Conference in 27 in November, where we hopefully see maybe first decisions on potential spectrum for 6G deployment. Also very important, and I will come back to this, we had this initial run as a workshop taking place in Korea in March 25, earlier this year, and already the first plenary meetings after that. So that's also the reason why we have this more detailed time plan now available to us. Good, that should serve as an introduction, and let's move on then maybe with the, this workshop that took place, this initial workshop, where all the companies could lay out their initial thinking on what 6G should serve for, what it should be, how it should be realized, maybe at least in terms of initial thoughts. Many companies had different strategy or even run concrete or core network concrete documents presented. I took that analysis from Antti Taskala from Nokia, who did and present that 5G ICAA. So he kind of analyzed all the buzzwords or the key items mentioned in the various contributions to that workshop. There were more than 700 delegates attending, and of course, a high number of documents coming. You see certainly that machine learning and end-to-end topics, maybe also digital twinning was at the top of a list on the most named topics, but you also see in that list something around terahertz, but also more importantly, maybe sub-6 gigahertz spectrum innovations, which is also maybe largely covering the subject on which waveform we are going to use for this new 6G technology to be specified. So when we talk about spectrum, which is, as I mentioned, kind of related to the waveform discussions, we initially had really also the interest in higher frequencies. It's been a bigger topic, I would say, in the early days of discussion on 6G. Ranging above 100 gigahertz, even up to 3 tera or so, but maybe with a focus on deep-band investigations around 300 gigahertz, maybe also. But I believe it's fair to say that in meanwhile, the interest in terms of initial deployment is rather in the what was initially called FR3 frequency range, more concretely maybe today in this 6 to 8 gigahertz range, or around 15 gigahertz as well. You see here some quotes that were even done or available before the workshop, where specific frequency bands were mentioned, also out of the Next G Alliance, out of the US, whereas this 12 gigahertz ranges are also in focus, maybe as a certain specific item in that region. But you see the interest of different companies, and I just took two of those. Of course, there are plenty of those people that have expressed their minds. I also like to highlight one more concrete example from an operator perspective on how far spectrum is important, which frequency they see in favor. I took the liberty of taking a German operator, because I'm coming out of the German country here. I think it's very important to see that 6G clearly has also the requirement to work in these frequency bands that we already operate, not only for 5G, but also for earlier generations. So anything starting from 410 megahertz up to 7 should be in principle possible to be operated also with the future 6G technology. I think that was a clear requirement, and it's often mentioned by many operators globally. You see a little bit of specific thinking of Deutsche Telekom here for the 6 to 7 gigahertz range, which has a certain potential in their view, whereas the rest, so between 7 and higher, up to 24 gigahertz, is not a potential seen from their perspective, at least not for Europe. Obviously, this is different in other regions of the world. There's also some mentioning for the FR2 frequency as a potential later on, but more or less kind of ruling out the higher frequencies, as I mentioned earlier, anything higher than 71, which is not seen really of interest for 6G radio deployments initially. So I guess you will find more information and different opinions, as I said, from different regions of the world, but I certainly think that in 6 to 8 gigahertz, we have a certain concentration of interest here. And that is having an impact on the waveform, in my view. So we have not only that reuse of FR1 spectrum requirement, we also have, and I think that was clearly expressed also through the earlier sessions in this conference, a clear request for a standalone operation of 6G, meaning that we don't want to repeat this non-standalone architecture where we operated LTE and 5G, different radios and different options, and this should be avoided this time so that we have a clear standalone 6G architecture involving radios and then of course a core network. And together with this requirement to reuse FR1 spectrum or existing spectrum, there is this solution of now called multi-rad spectrum sharing, something similar we had already in 4G times called dynamic spectrum sharing that they or these days, and it was for operating 4G and 5G, or more precisely 5G in 4G spectrum. That was a little bit more cumbersome because 4G has quite a lot of always on signals. This is much better than 5G, and people see here quite a nice potential to allow to squeeze out free slots, free parts in the time frame for 6G operating in that existing 5G deployments, and for that allowing this refarming of FR1 spectrum, but also allowing support for such solutions. Also, I'm thinking is motivating a certain similarity what we operate in 5G today. The summary of the chairman on that initial workshop on the radio interface was this quote. I just put it here on the slide. You can see that also in the official documents. That a non-backwards compatible, at least from a USB perspective, is foreseen to explore really full potential. However, with certain characteristics like in waveform, like modulation, channel coding, based on what we have in 5G and R today. I think it reflects a little bit this motivation, and also this one reason why we have a certain discussions towards OFDM systems for 6G. What else did we have on the table as a proposal? I mean, There is one more concrete proposal brought in, I think this is from Samsung in that workshop, which is describing also an OFDM-based system, but with an extension. You can see these green blocks here that are proposed to be added. So essentially, we extend the spectrum usage in terms of subcarriers to be used, even larger than the band that is foreseen, and also putting on top of that a certain filtering, a certain shaping of these subcarriers. And the motivation for doing so is essentially to lower the peak to average ratio of such waveforms. And obviously, this is one of the disadvantages we have when we operate OFDM systems, that we have quite a large peak to average ratio, which requires us to lower the average power of the power amplifiers, not being able to operate them at too high power levels. And obviously, this is specifically in the uplink having an impact on the coverage and also on the performance. And for that reason, they are looking for these improvements in peak to average ratio, and this is one potential, at least according to their analysis, and it is part of the discussion. Also, as an input to this workshop, there was an IndiaNote document, I guess. It's the name for this waveform was orthogonal time frequency division multiplexing, OFDM. And you see fairly similar concept also. So after the MNDFT, you also see the excess subcarrier as a spectrum shaping filter proposal. So I would say this is the same concept in the sense that we just saw. There are, however, more changes proposed. So I put all the resources where these schemes are described here also on the slide, the input document to the workshop, as well as scientific publications. And there you will find there's also some additions and modifications to the time domain, which I, in the interest of time, will not explain in much more detail here. But this is going beyond this scheme that we just saw from the earlier proposal. But it's also having a similar part in it as that we saw before. So these are the, I would say, OFDM-based kind of proposals that are on the table. And obviously, with the study item phase that is coming now in round one, we will see a larger discussion. We should not forget that we have, and that was mentioned also by the introduction here already, that we have alternative schemes that have been discussed already for quite a while. So maybe most famous one is the OTFS, which is then going to the delayed Doppler domain, which has really advantages specifically for the high speeds. I think I don't need to explain all the details of that using the exact transform or even alternative ones and how to design it. It's really known. You can see the first mentioning of that proposal was already back in 2016. So it was part of the discussions early 5G. They made it into the specification at that time, but it's brought up again here. And yes, as we said, for specific scenarios, there might be advantages for using such a scheme on the physical layer. So it should not be forgotten here. So summing that up to a certain extent and sharing what our view is, maybe a certain working assumption we think. So I believe it's fair to say that there is a certain tendency, at least by industry players, maybe mostly the established ones, to stay to CP-OFDM or DFTS OFDM in uplink and downlink, and then maybe have a little bit of a modifications or enhancements like we saw from the shaping. But there's at the same time a little bit of an acknowledgement that there is an ongoing discussion whether we need specific waveforms for specific use cases. Satellite NTN was mentioned, ISAC was mentioned here and there. We have the zero energy devices that maybe have the clear requirement for something different than we have in OFDM. So there might be arguments for doing something specific for these use cases, although the market size of these different additional use cases, of course, needs to be big enough to justify the efforts that we are spending for that. And we should also not forget that there is an additional angle in terms of waveform that is discussed, researched, and this is all in relation to machine learning solutions. So you can think of learning waveforms for specific environments, so to adapt really to the best possible in whatever street, whatever area you want to operate your system, and really allowing this more detailed local adaptations. Again, some references here for you to read that up, but there's a lot of things ongoing. And when we talk about this modification of waveforms, I just really shortly like to reflect what people are doing, because to relate it to this, we have this neural receiver work, right? If you look to our transmitter receiver chain here with blocks like channel coding, scrambling, and so on, essentially, obviously, we can exchange each of these blocks that are solved by algorithms today with a machine learning block. The initial work was very much done on neural receivers, where just on the receiver side, we were coupling demodulation, channel acquisition, channel estimation into a single block, and based on convolution networks, realizing a neural receiver, which was quite performant, and even in certain environments outperforming the classical algorithms. That has been developed further towards optimization, not only on the receiver side, but in combination with the transmitter, so allowing for custom constellations, not the traditional QPSK, 16 QAM, whatever we know, but something very specific for that specific environment. That is ongoing work in terms of really optimizing something for specific environments, and it's not on paper only. You see here something example where they came out with a certain or trained a certain constellation. You see it on the screen of the instrument as well as at the enlarged screen on the Samsung side, that this constellation diagram is not really QPSK, 16 QAM, whatever anymore, but something very specific in this specific trained case. So that's interesting, and also may play a role in defining waveforms in future. But as I said, I think we have a starting point, which is kind of OFDM based. Now, just I'll let you know a little bit how we test these things these days. So you usually have, and I like to illustrate that a little bit more. We have this, and how this is already reality, maybe in terms of research work, pre-development work that is ongoing right now. There's a little bit more information. You see that on the top of the slide. But if you have a certain instrument from any of the test and measurement vendors these days, then we have, of course, these specific options that reflect usage of the known technologies like 5G or earlier ones. What we recently did is shown here in the small video, so we can have, of course, a certain number of modulation points being installed, and then we can enable custom constellation. And of course, our engineers made a little bit of a fun of it. You can see this nice constellation diagram on the lower right on the spectrum analyzer now. We just need to search for the environment where this modulation scheme is going to be the best one for. That is, of course, just a showcase example, but it shows you that this enabling of custom constellations and maybe any other way of more adaptive waveforms is in the real works at the moment. Same is true for the OFDM-based work. So here, another thing where we go to higher frequency, but it, of course, does not need to be higher frequency, where certain software allows you to set certain subcarrier spacings, number of subcarriers, and cyclic prefix lengths to experiment with a different parameterization of the OFDM signals. Certainly, this is focus of the work right now. That can be equally in the time domain, allocate data and pilot signals and so on. All this is done and used with you enable that transmitted. You can, of course, again, measure the spectrum, or going to some more detailed OFDM analysis software, you will be able to measure your EVM according to the signal characteristics just played out. And then, of course, you will send that across real devices like PAs, whatever you want to investigate. So this just should give you an impression that this is ongoing real work, reflecting the interest in these different ways of analyzing this stuff. Not to forget about OFDSS, OTFSS, which was also demonstrated already. So this is nothing new. So with that, maybe let me conclude with a kind of a high-level picture of how we see the network in 6G being evolving. So on the network side, a lot of things that are important, not only waveform, and I really like to highlight that waveform is just one, not unimportant, but important, certainly, aspect, but there are so many others that will reflect the 6G system as such. The capability like sensing, the satellite access, or the non-terrestrial support, the emphasis on energy awareness, like security as well, open interfaces, and maybe something like XR application that hopefully drive that deployment forward in future. So this is kind of a summary of my talk, and I'm at the end. So I'd like to thank you for the attendance, and of course I'm very open for all your questions that you may have. Thank you so much.
Okay. Thank you, Mr. Kemp. Thanks for the wonderful session. I think it was very enlightening, and also I think it was a good session to start with. So thanks for the whole thing. I think Q&As we will take it up at the end of all the sessions. And thanks again. In the meantime, we will invite our next esteemed speaker. So if you can present the slides, please. Vaishali. Vaishali, is the slides coming up? Yeah, sorry. No. Okay. So again, after having a wonderful session, a wonderful presentation by Mr. Kemp, by Mr. Mick on OFDM on OFDM, I think we are heading to our second presentation by Professor Radhakrishna Ganti. So Professor Radha, the second presentation will be on a very interesting topic actually. Basically, it will be like where the whole dilemma of this whole session, what we're talking about, like the OFDM dilemma is there, or there's a potential new waveform for 6G exists. So this is also this session is particularly looking for, is OFDM here to stay or not? So I think it'll be an interesting session. Thanks to Dr. Radhakrishna Ganti. About Dr. Ganti, he's a professor from IIT Madras, Chennai, and his research interests includes digital communication, convex optimizations, cellular systems, and building communication systems. He was involved in development of 5G base station for the 5G testbed project funded by DOT, and is currently involved in the development of 6 terahertz testbeds. Sorry. And in 2019, he was awarded the TSDSA Fellow for Technical Excellence in Standardization Activities in Contribution to LMLC use case in ITU. So I hereby welcome Dr. Ganti and to present his and express his views on whether OFDM is here to stay or not. Dr. Ganti.
Thank you, Pradeep. So the slides, TSDSI will be presenting. I sent them the slides, I think so.
Yeah, there will be. One second.
Yeah, thank you. Just let them pull up the slides.
Put up the slides from Dr. Ganti. Yeah, it's visible. Thank you.
Yeah.
Dr. Ganti, please.
Yeah. First, I'd like to thank Prakash and Pradeep for having me here. So when Prakash asked me, you want to debate about OFDM, I readily said yes. Okay. So I just want to, this is of course a provocative title, is OFDM here to stay? So I want to look at how OFDM evolved and what are its strengths and weaknesses and how will it fit in 6G. Okay, that's going to be the goal of my talk. I have to thank my postdoc, Dr. Anil Y. Am I audible?
Sorry to interrupt. Yeah, you're audible, but your camera is a little bit quite dark. Are you in a, I don't know, we are unable to see your face. I just see a blank screen.
I think I'll just switch off my camera for some reason. Maybe it may not be working.
Sure, no issues.
Maybe because
No
of HT. Okay, I'll just.
Sorry to interrupt. Please continue. Thank you.
Yeah, thanks to my postdoc. So I last few days I was actually researching how OFDM actually started. After I read that, I felt that I want to quote one Telugu thing, Tyagaraja Kruti, Endaro Mahanubhavalu Andariki Vandanamalu. So it says that we stand on the shoulders of giants and salutations to them. Actually, it's truly humiliating when we start reading the history of OFDM. Next slide, please. So it also all the way starts at Graham Bell, 1870. I've listed 3 patents. So initially, after the Graham Bell's transmission over the Atlantic, they wanted to do multi-tone transmission. Okay, so essentially that is the genesis for FDM. You can see like how at this point people are fighting for waveforms. You can see 3 people. One is Graham Bell, Elisha Gray, and of course Thomas Edison. All of them trying to do similar things, fighting for multi-tone transmission. It was a very interesting thing. So they succeeded to a certain extent. You can see the Morse code there. After that, the FDM was actually been this whole notion of FDM, which is the genesis of OFDM, frequency division multiplexing. George, a major in the US Army Signal Corps, in 1910 has made the first FDM system. Okay, this is for Signal Corps mainly as an anti-jamming system. Okay. So then from 1910, it was mainly a military technology. In 1918, AT&T developed the first 5-channel FDM. Okay, so essentially they took 5 channels. If I'm not mistaken, the whole bandwidth was about 3 kilohertz. Okay, so so then it became a main multiplexing strategy for telephony for a long time. Okay, so it all the way started. This whole battle started in 1870. Next slide, please. Just 1 minute. So the history, so essentially there's a beautiful paper on the history of OFDM in IEEE Communication Magazine. I would strongly recommend you to read this. That's what I'm taking a lot of my slides from. Next slide, please. Okay. So you can see the, so in 1960, this was called the N2 carrier system. There are 12 telephone subchannels, 8 kilohertz subcarrier spacing. Okay, you can see the 8 kilohertz subcarrier spacing, but the actual bandwidth per each subcarrier that can be used was 4 kilohertz. The other 4 kilohertz was the guard bands that have been wasted. Okay, so if you look at this, this looks exactly like how our OFDM looks, except for the guard bands. So, so between 1980 and 1960, things were a little bit slow. I'll explain you one more thing in the next slide. In 1970s, when the digital telephony started, it was like the telephone in which you can press buttons and signals have to go. So that is when FDM first time got challenged by TDM. So up to that point, most of the multiplexing was done through frequency division multiplexing. Only when these phones with buttons came in 1970, people started thinking that TDM is also necessary. So essentially the FDM channels that the AT&T Bell Labs have proposed have gotten replaced with TDM and FDM, FDM, and pure, there should be pure TDM, not FDM, sorry, and pure FDM, and pure TDM. Okay, so at this point, they made one interesting observation, 1970s. They said that faster data rate will require larger bandwidth. And when you have larger bandwidth, either through wire or wireless, you have higher selective fading. This is for the fading that you see in a channel. And this will require more subcarriers. Okay, so essentially this is observation they made, but unfortunately at that point, they realized that FDM also wastes too much resources for guard bands, as you see on the top. And to do this on a PCB or electronic circuits, the circuits were pretty complex at that point. Next slide, please. Okay. At this point in 1942, it's a very interesting thing. So frequency hopping also came into picture. This frequency hopping was made by Hedy Keisler. You can see her photo. She later became a movie actress. So it's exactly, it looks very similar to our OFDM, except that since they did not have this FFT-based circuits and other things, what they did was they used a hardware oscillator which moved from one frequency to another frequency, which are harmonics of each other, to do the frequency hopping. And this is the same thing. Similar technology was what was developed by Flareon. That's called the Flareon flash, in which users' allocations moved quite a bit in the frequency domain. Of course, now this has been acquired by Qualcomm, and that was mainly to minimize interference. So this idea of minimizing interference through FDM movement was known all the way at 1942 almost. Next slide, please. Okay. The way we think about OFDM, Bell Labs, the way we visualize OFDM as subcarriers and doing things in the way we do right now, effectively came in 1970 by Dr. Chan. Essentially, he designed the first multi-carrier modulation scheme using overlap. So essentially, if you understand OFDM has multi-carrier modulation in which things are orthogonal, but they overlap. Okay, the orthogonality helps to decouple them, but they still overlap. And they're non-interference. So exactly this is the same thing that we are talking about OFDM in 1970s. And Strasberg quantified the performance benefits of this. Both of them are from Bell Labs. So again, they are the pioneers of this. At similar time, when this was happening, you can see down, I put a picture. That picture is the first high-frequency radio OFDM system. Here, they did not have proper DSPs or digital circuits to implement them. They implemented the entire OFDM. Okay, this is 34 channels with 3 kilohertz bandwidth. So essentially, each of them is 3 kilohertz by 34 is the subcarrier spacing. Okay, you can see the TDMA structure and the frequency domain structure. This is exactly the time frequency grid. So they implemented this all in analog circuits. I mean, it's just amazing how they were able to do this. Next slide, please. Okay. At the same time, in 1971, again, these are part of the Bell Labs. They realized that the FFT that has been invented around that time can be applied to do OFDM. Okay, so this was the genesis of the modern OFDM. But when they did that and they wrote a publication, they were absolutely no interest in this technology. Even Bell Labs people felt that it was not a big technology. A patent was not even filed. Okay, 1971. The same time as the other things were happening. So after that, for approximately 20 years, almost nothing happened. Next slide, please. And then ADSL came. So at that point, Bell was studying both OFDM and CAP. CAP is carrierless amplitude phase modulation, a single carrier system with certain modifications. And they choose CAP instead of OFDM because it was easy to implement. Okay. So at that point, Professor John Chaffee from Stanford felt that, okay, the multi-carrier systems are the way to go. And he had a company called Amati. So they essentially developed OFDM. I shouldn't say it's OFDM, it's OFDM with bit loading. Okay. So, and they had a competition with the CAP system. And they won the competition, and that brought OFDM back into limelight. And it turns out the early adapters are OFDM. So they have done this for ADSL mode, DSL and ADSL. And the early adapters of ADSL was France, Britain, and Australia. And that later US adopted this in 1997 after a few years, after 7 years. And then TI purchased this Amati. So one thing what Chaffee, if you look at his notes also at this point, tells you, the reason why OFDM is so OFDM with bit loading, okay, that's very a little bit different from the way we do OFDM in wireless, okay, where we don't change the power of the subcarriers. We keep the power of the subcarriers the same. We change the code rate, the modulation of the subcarriers. But in ADSL, they change the power of the subcarriers also. Essentially, it's done through something called inverse waterfalling. So essentially, you gain capacity by betting on the channels which are good. You put all your power on the good channels, and that's why you get capacity. Okay, so that's what their main idea was. Next slide, please. And from 2000 to present, we all know now OFDM, after all that, after Chaffee showed that this is very, very much feasible. Of course, it came into Wi-Fi, ADSL next versions, WiMAX, DVB2, LTE, 5G, NR. And of course, all of this also got married with the advances in, MIMO, as well as forward error correction codes. Okay, so generally OFDM by itself it's a waveform, but it does not make sense. OFDM, when only married with the coding, gives performance. I say it's capacity. What you say is capacity achieving in terms of information theory. Okay. Next slide, please. Okay. So now I'll come back to this question. Why should we rethink the waveform for 6G? I mean, is it even necessary? So the arguments that a lot of people make are it should support high frequencies and bandwidths. It should improve energy efficiency. The main problem is the PAPR. The previous speaker also alluded to. It should support high mobility scenarios, robust to Doppler. Okay, you want to drive vehicles at 2,000 kilometers per hour. So then what happens? Reduced overhead and latency. And you want to do a lot of things. You want to do sense. You want to do non-terrestrial networks. You want to connect terrestrially. You want to do IoT. You want to do everything. Okay. And on top of that, essentially, we also want to really cover people. Okay, so I mean, I think that should be the first point, but and unfortunately, that's the last point. But people talk about that we want enhanced coverage. Okay, and these are the things that people say. I mean, can OFDM do this? Okay, so next question, next slide, please. Okay, so my case for OFDM is this. Okay, so it's a beautiful technology. Okay, it's a multi-carrier modulation essentially that takes a wide band, divides into smaller chunks, and essentially you have multiple parallel channels, either both in time and frequency that you fill up with whatever you want. You can fill up with pilots, you can fill up with data, you can fill up with signaling, you can do whatever you want. Okay, and all these subcarriers are orthogonal. Okay, so this is the main thing that I mean, essentially, if you look at the 5G spec or the 6G, I mean, are going to the 6G spec. Essentially, you are going to talk only about how do you fill this resource grid. And this has been used. This has been used in so many. It has been tested to death. It's used in so many standards. And from a very technical perspective, this is a capacity achieving waveform. Okay, if you have frequency selective channel, OFDM with power loading or rate loading is the capacity achieving. Period. There's no second guessing it. Next slide, please. Okay, what are the strengths of OFDM? Why? Why did it survive so many decades of assault, and how could it become so successful? Essentially, it provides extreme frequency diversity. When you couple it with interleaving and FEC, it's just so beautiful. It's multipath resistance, a very high spectral efficiency because it's tightly packed orthogonal subcarriers. It's reliable because it's reliable both in terms of timing as well as multipath fading. It has scalable bandwidth. Essentially, you have, I mean, of course, this has been misused in 5G. I mean, multiple numerologies can be defined. The most important thing for any practitioner is the equalization, channel equalization. You take any single carrier system, once it crosses a certain bandwidth, equalizing that is a nightmare. Okay, people who have built single carrier time domain systems understand this. Equalization in OFDM is such a beautiful, nice thing. It's such a pleasure to work on it. And of course, efficient hardware implementation because of FFTs. And now, so there are so many chips that can do FFT at such low power that it's almost impossible to beat them. And it, of course, works well. It tested over billions and billions of devices, and so the law of inertia holds true. Next slide, please. So the two main variants of OFDM in 5G, one and 5G and 4G, CP OFDM, which is a downlink waveform, and the DFT spread OFDM, which is the uplink waveform. Okay, so in the downlink waveform, the CP OFDM is used both for uplink and downlink in 5G, of course. And the DFT spread OFDM is, of course, optional in uplink. That is a mistake that I think people have done. So essentially, if you look at CP OFDM, it's high PAPR, it's good low complexity, but it's mainly dealt for base station kind of implementation, whereas DFT spread OFDM is mainly for UV kind of implementation. Next slide, please. Okay, so what are the drawbacks of OFDM? Essentially, it's high PAPR. Okay, I mean, again, I'll come back to this point, high PAPR. I mean, it's overly done. Sensitivity to synchronization errors, essentially, it's very frequency selective. You have to have good oscillators, and of course, you can't run too fast with your mobile. It has out-of-band emissions. Essentially, it requires some filtering like VOLA or something to meet the spectral mask requirements. And there is also an argument that these are not suitable for very high mobility scenarios. Again, So this you have to take it with a pinch of salt. It's not exactly what is meant by high mobility scenarios and what is the pilot structures you have. It depends on a lot of things. It's just not like an open statement you can make that OFDM and DFT spread OFDM are not suitable for high mobility. That's not correct. Next slide, please. Okay, so this is a small comparison of so essentially this x-axis, this interesting graph. See, this is taken from a paper, OTFS versus OFDM in the presence of sparsity, a fair comparison, written by Chris Baker. He is an excellent author. So, here you see down on the x-axis is the Doppler versus the Doppler normalized by the subcarrier spacing. You see that if you are below 15% of your subcarrier spacing in terms of Doppler frequency, then there's no difference between OFDM and OFDFS. And 15 kilohertz and 10% of 30 kilohertz is like 3 kilohertz. And to achieve 3 kilohertz, you have to really run at almost 1,000 kilometers per hour. Okay. So in that way, I mean, I understand OTFS, of course, I mean, this is also a little bit exaggerated. OTFS does provide some gains when you really have mobility. But I don't see that it really OFDM performs so bad. I'm not going to comment on OTFS performance, but OFDM performance in high mobility, specifically when your pilot structures are taken care into consideration, is not such a bad performance. Of course, if you want to drive at 10,000 kilometers per hour or you want to use missiles with OFDM, then it's a different game. Next slide, please. So OTFS, I'm not going to go into this. This has been also covered by my previous speaker. I mean, it works in the delay Doppler thing. It can resolve delays and Dopplers very, very well. Next slide, please. Next slide. So it's a compact and sparse representation of wireless channels. It's a very nice mathematical representation. And people are saying that this is very suitable for ISAC and V2X. It embeds information in the delay Doppler thing. Its main challenges as of now that has not been resolved to a certain extent are the fractional delays and fractional Dopplers. It increases the complexity of the system a little bit, but I think there are some solutions to this also. Next slide, please. The third thing is the OTFDM, orthogonal time frequency division multiplexing. So this is like a souped up version of the DFT spread OFDM. Essentially, this allows this gives a low PAPR, low latency, and it also helps out to put all modulations on the upline. Okay, so this is similar to DFT spread OFDM. I still call this an OFDM waveform, even the name says so. So I'm not going to dwell much into this. The previous speaker also read. It's actually a nice thing for uplink. Next slide, please. Okay, so what are the parameters to evaluate a waveform? I'll take a couple of minutes. One is scalability. Essentially, multiple channels. I mean, if you look at 5G, there are multiple channels, control channels, initial access channels, patch, SSBs, you name. So there's so many acronyms that you have to fit in the channels. Okay, and they should also work with multiple applications, communications, sensing. It should be mixing with non-terrestrial networks. Okay. Other major thing that a lot of people don't talk about is how do all these waveforms integrate with MIMO. MIMO and OFDM are a marriage made in heaven. Okay, so it works so well. The moment you don't have decoupling of carriers, this multipath, doing MIMO with multipath channels is again a very, very complicated thing that it's difficult. Okay, and it should be, of course, be robustness to channel conditions, work in high mobility scenarios, equalization issues, multipath. And it should serve XR, VR, all sorts of future generation standard. And finally, it should be easy to implement. Finally, all these things should be implementable. It should be implementable in a power efficient manner. So these are some of the parameters that you have to look at while you evaluate a waveform. At least my opinion is no waveform will fit all those things. Things that can do NTN. Of course, OFDM is still using NTN, but it's not the best waveform NTN because of the PAPR issue and other things. But saying that, again, it depends on what kind of things are you looking. If you looked at fixed wireless access, then PAPR is not such a big issue. Okay, next slide, please. Okay, so these are my thoughts. Okay, 6G's main frequency is going to be from 6.5 to 11.5 at 12 gigahertz. Okay, that is what 6G is being told. So that is mainly an FWA application. In FWA, I mean, the name itself says mobility is not a big deal. Okay, mobility is not a big deal because, and I mean, I don't think you are also going to do FWA over 110 multiple kilometers. So, so there's no mobility. So the issue of Doppler and other things may not be such a big issues in these frequencies. Okay, and high-speed mobility, OFDM has issues after 500 kilometers per hour. OFDM works in 5G and it has been designed for 500. But if you want to put this in aeroplanes and other things, then you might have to look at a different waveform. Non-terrestrial networks, again, how big a part are non-terrestrial networks of 6G? We have to understand this. The capacity provided by NTN is really unknown. It's mainly for doing coverage in places where there's really no accessibility. PIPR is an issue, might require a new waveform here. IoT is a completely different game. This has nothing to do with OFDM or DFT spread OFDM. It has something to do with 5G. 5G is 6G is a too heavy waveform for IoT. Okay, if IoT have to really succeed, it has to be a very, very, very simple waveform. If you look at LoRa or Zigbee or any of those things, that's the type of waveforms you require. They're on-off keying, chirp signals kind of a thing. ISAC, at least my personal opinion is ISAC waveform is not going to be the bottleneck. There are so many other issues in which ISAC to work upon. I don't think, I mean, essentially, realistically getting 5 to 10 meter accuracies in these deployments would be really be nice in outdoor units. And I think OFDM works very well for that. And my thing is that waveform will not be the bottleneck and other issues will be other things that you have to take care for ISAC. Next slide, please. So my opinion for the debate is that OFDM has still a few more, at least a decade left, has some time left. I think we should squeeze some more things there. Thank you.
Thank you, Professor Gandhi. Definitely. So it was very nicely put up that OFDM has still time left. So I think we need to explore that further. Maybe there's some more juice left to squeeze in further. But nice points put up. We will definitely, and very well covered right from the history of the waveforms all the way till OFDM, different forms of waveforms, and where OFDM may lack, but still, there's an applications needed. And since OFDM has been proven till 500 km per hour, it may still have time. So, but anyway, we'll come to that. We would like to hear some more views from our other esteemed speakers. So once again, thank you, Professor Ganti, for your time and sharing your views. So now I welcome Mr. Satish Jamadagni to share his opinion on 6G waveforms and the way forward for India. Mr. Satish Jamadagni is currently a Senior Vice President and Head of Global Standards at Reliance Jio. If you can help me put the slides back, I would like to, I'm still introducing Mr. Satish Jamadagni. Yeah, thank you. Yeah, he has about 25 years of industrial experience in the telecom domain. He is a veteran here, very well known for many of us here. He's currently is chair of TSDSI. He was also previously a vice chair of TSDSI. He is active in 3GPP, GSMA, member of a strategy group, and in Orion Alliance as well. Earlier, he was a co-chair for the Asia Regional Operators Group, Small Cell Forum, and was on the board of International Multimedia Telecommunication Consortium, IMTC. So I hereby welcome Mr. Satish Jamadagni to kindly share his views and present his notes on the particular topic on 6G waveforms, the way forward for India. Satish, over to you.
Thank you. You can hear me, right?
Yes, Satish, we can hear you. Thank you.
So when I realized I'm the third speaker in a list of 3 speakers, I just thought I should stick to practicality and cut out all the technical information, because I think both the previous speakers did a very good job of introducing what OFDM is all about and what is the way forward. So coming to practicalities, I mean, primarily learnings from 5G. Why is it that, at least I'm not very enthusiastic about OFDM as a waveform for 6G? Primarily comes from the fact that IG, one of the biggest issues that we face is coverage. It's nothing to do with, or one can argue, I mean, it's nothing to do with waveform itself per se. There are quite a few other issues also to be taken into account. But whatever it is, practically 5G has some serious issues, both in terms of coverage. And what that means is the amount of money spent by operators for the same coverage as what LTE provides today is something in the order of 5x. That's a pretty large investment to go into just for the heck of coverage. So the other issues also in 5G, millimeter wave issues, multi-user MIMO has not necessarily been giving any level of gains. It's I'm speaking for a lot of operators. It's not just Reliance Jio. This is some of the learnings that is coming out of a whole bunch of operators that I have been speaking to. So there are a few things to note, especially when we talk about 6G. So 6G is not necessarily about EMBB. When we talk of 5G, essentially we are talking of EMBB, broadband connectivity. That's all that we are talking about. We're not talking about verticals. And I think in 6G, with OFDM, without OFDM, whatever it is, this is a key distinction that will have to be brought into. And yeah, OFDM has 2 generations. Again, third generation is OFDM. This is happening for the first time. I'm not saying good, bad, or ugly, but yeah, that's what it is. So here's a list of use cases and some of the KPIs. I think Radhakrishna also covered this. So the key takeaway from this is that each of the vertical, if you treat EMBB also as a vertical, has its own characteristics. So primarily one single waveform, OFDM or otherwise, is not going to cut like what we tried to do in 5G. 5G, everything was force-fitted, including NTN. A terrestrial waveform was an NTN spec was written on top of what was essentially a terrestrial technology. And there are efficiency issues that come into picture. But anyway, so these are some of the aspects which Radhakrishnan also has covered. ISAC, for all practical purposes, you can have a separate radar independent of your MIMO system, your essential communication system. And that's a different question altogether as to how that can be managed. May not necessarily be just the issue of waveform, but then waveform is also one of the critical issues here. What is it that we are trying to do here, which can at least bring the singular implementation of ISAC and your communication in a single base station? That's the whole objective. I mean, if that objective is left out, then essentially you're putting a radar on top of, or a camera for all practical purposes, on top of a tower, which is perfectly fine. And even for industrial IoT, there are other issues which will come into picture. Then again, yeah, there was a comment saying that a simple waveform will do. Yeah, for IoT, one does not necessarily have to have a complex waveform. And NOMA was discussed when in 5G, for whatever reason, it did not go forward. Similarly, for broadcast, ATSC 3.0 uses coded OFDM. So, yeah, I mean, OFDM has been around for quite some time. Looks like it is going to hang around for quite some time. But whatever it is, there was a big statement which was made in the recent RAN plenary, which was encoded. I've shown it in the slide. Waveform OFDM based. This is explicitly written. So, when we look at the scope of the study which has been approved as part of the 3GPP RAN working group, looks like there's not much of a space for any other waveforms other than OFDM based. Now, practically, there are quite a few questions which come into picture. I mean, it doesn't matter if it is DFTS, OFDM, OTFDM, small variations here and there. Spectral efficiency and PAPR are the 2 key issues. PAPR really, I mean, it's just a fixed entity. It does not necessarily change, at least from an operator perspective. We're not expecting, any increase in PAPR adding to anything else. There's a minimal threshold which has to be met, and I think that's already been met. when it comes to spectral efficiency, that's not necessarily the case. If you look at the IMT 2030 specifications, people are adding numbers to the spectral efficiency variable. When that has to be taken into account, any variations in OFDM, be it OTFDM, which can bring certain amount of Doppler sensing into MIMO efficiencies, or DFTS OFDM, which is already non-mandatory waveform in 5G. You start wondering what is it that 6G will bring onto the table in terms of overall efficiency in comparison to 5G. What is it that 6G will bring onto the table? And there are other things which are today wrong with massive MIMO. I mean, though this is a discussion about waveform, for all practical purposes, we do have to talk of massive MIMO efficiency. One has to feed to the other. Unless that happens, then the discussion is not complete. So today we have a serious issue with multi-user MIMO. May not necessarily have anything to do with the waveform, but then other technologies like pairing is a critical issue which needs to be sorted out. And then again, if you look at 6G, the amount of base bandwidth is going to increase. It's not 100 megahertz. It's going to be orders of magnitude much higher than this. The other issues which will have to be taken into account, one of that is beam squint. But there is always a question of what is the threshold beyond which this kicks in. And these are all the uncertainties which will have to be handled in the 6G waveform, OFDM or otherwise. So, given the fact that the RAN plenary has more or less put it in stone that OFDM waveform variants are the ones which are going to be considered for 6G, at least the steady part, yet to be seen whether it gets into practicality, but at least steady part. The goodness is something that will have to be seen. So more or less, even if there is a certain amount of efficiency which comes onto the table, if it's about 10 to 20% more efficiency, some of which will be eaten away in the implementation inefficiencies, trust me, this is not exciting for operators to look at. And that is the key message. So sometimes when I think of what is the way forward in terms of 6G waveforms, there are a few things that will have to be on the priority table. One is different waveforms for different verticals, coexisting or not, may not necessarily be a big issue, but that is something that has to be discussed. Multiple coexisting waveforms, OFDM or otherwise, is something that has to be discussed. Then MIMO efficiency is the key aspect which can bring in coverage and capacity, or can address coverage and capacity concern, specifically capacity. Coverage, there are still other technologies which can be pulled up, like for example RIS, but capacity issue at least has to be addressed if you start going up higher in the order of MIMO. So specific waveforms for specific verticals, is that what we should be looking at? EMBB, just keep whatever we have in 5G. We just focus on getting MIMO right in 6G, because 5G is still, there's a lot of struggle as far as MIMO efficiencies are concerned. So this is the thought process I have. When I think of, what is the way forward, should we just forget about 6G waveform, at least for EMBB, and think of specific waveforms for specific verticals, and just focus on getting MIMO right for 6G EMBB. This is the thought process. And most of the technicalities have already been presented by others. So with this thought process, I'd like to end my presentation. Thank you.
Great. Thanks, Satish. Thanks for your opinions and your views. Definitely, it was giving us more practical views as a way forward, from today's situation. So thanks for it. And with this, I think we conclude our three keynote presentations from three of our esteemed speakers. Once again, thank you all. I would like to now hand over to Mr. Prakash, who will be moderating the coming up panel discussion. Thank you all again. Prakash, over to you, please.
Thank you, Pradeep. And thanks to the speakers for the three wonderful talks, which sort of brings a lot of questions, which I propose to continue. So let me now introduce the three of the speakers are introduced. Let me introduce the remaining speakers. Can we flash Mr. Charles Santosham, who is a senior management. The fourth speaker for the panel is Mr. Charles Santosham, who is a senior R&D management professional with 28 years of wireless experience in L1, L2, L3 architecture system engineering. He has been working on the development of software firmware on CPU, DSP, FPGA, GPU-based computes for all generations of mobile from 2G to 5G. He's currently leading the aerial development of aerial L1, L2 offloading on GPU for 5G, 6G wireless in India as part of NVIDIA. So welcome, Charles. I request all speakers to enable their cameras so that, normally we invite people on stage, but since we don't have stage, I request all of you to enable your cameras. So the next speaker, please. So the next speaker I would like to invite is Dr. Vivek Chowdhury. So Professor Vivek Chowdhury is an assistant professor at Gautam Buddha University, Greater Noida, where he leads research on enhancing security and efficiency of next generation wireless communication systems. His work spans novel waveform design, full duplex radio architectures, and the convergence of sensing and communication technologies to elevate network performance and maximize resource. So thank you for joining us, Dr. Vivek, and welcome on the panel. Can we go to the next slide? So the next speaker is Mr. Mohammed Saeed Mombasawala. So Mr. Mombasawala is the CTO at Keysight Technologies India Private Limited. He's heading a team of industry experts in commercial communications, network security testing, memory and peripheral interconnects, as well as automotive energy solutions. He is a bachelor from EC at NIT Surat, and he's also got a postgraduate diploma in business management from IGNOU. So welcome. Thank you, Mr. Mombasawala. The next speaker, please. So the next speaker is Professor Kiran Kuchi. He's the founder of WISIC. So Professor Kiran Kuchi is a key member of India's 6G task force leading the national effort in 5G advance and 6G standardization and advising the government on strategy. With 200 plus international patents, including several essential to 5G, has significantly advanced wireless technology. He founded WISIC Networks, a startup at IIT Hyderabad, which has developed 5G base station, narrowband IoT system on chip solutions for terrestrial and satellite use. Okay. Thank you, Professor Kuchi, for joining. Next. Okay. So can we go back to the whole slide? Okay. Fine. We also have Dr. Meek Kotkamp from Roden Schwartz, who was also, I think the photograph is missing, but are the three speakers and the four new who are introduced here. Thanks, all of you. I'm audible to all of you. I hope all of you, if possible, do switch on the camera. So my first question is to Dr. Meek Kotkamp. So given, we've seen we have been talking about waveforms, but maybe a little bit, again, you did give a presentation, but I would like to ask you, maybe shall we go back a little bit, starting from 2G, 3G, and then sort of come to this 4G, 5G, and where do waveforms, where does waveform come in the overall communication industry, and why should we all discuss waveform? What is so important about waveform?
Yeah, good question, of course. So really, I think when we go as back as the 2G timeframes, I mean, that was time where we created a cellular system, and of course, the importance of these cellular systems were not really foreseeable yet. I mean, we had also this different schemes in US, IS-95, BTC in Japan, and even in Europe coming up, the GSM stuff. Well, there was the waveform, I guess, the physical layer as such was part of the whole system that was created. I think there we did not have a real big waveform discussion. Then where it was really a strong discussion was in 3G times, right? When we started discussing CDMA, even OFDM was in the creation these early days. And it was a strong physical discussion on which layer to use, which waveform to use, which access scheme to use. And that ended up even in a voting process that we never had before in 3GP, right? Or so what a tense discussion. Whereas in 4G, 5G, we moved then into this OFDM kind of funnel where everything was centric OFDM that had we pre-evaluated in 3G times, but then came through in 4G times and stayed until from there. So yes, it's important, but it was mentioned before. I mean, it's maybe not only the waveform, it's also the access schemes, maybe the antenna technologies like MIMO that have become more and more important to achieve the capacity that we need that play a role in combination with the waveform, right? So yes, it's important to have a discussion on the waveform, but certainly we have a cellular system with so many components also in the core network side and in interfaces and stuff that waveform can only be part of the discussion for the whole system. But coming back, I guess it's a smaller discussion than compared to 3G times, but we have that discussion with this preset already, as mentioned before by the speaker, seems to be already kind of agreed that we start with OFDM and 6G. Being right or not, that's kind of something that we see happening at the moment. And obviously needs strong motivation now to come up with something different, maybe for either technical requirements or market requirements to address certain use cases that are important and deliver certain market as well.
Thank you, Dr. Meek. So my second question is to Professor Radhakrishna. So you gave us a history of the waveforms of the OFDM evolution. Now, could you maybe contrast the uplink versus downlink? Why are they so different? Why can't we have the same waveform both in the uplink and downlink? And if you contrast it, is there any other waveform we could have put which should have had the same performance on both directions?
So thank you, Prakash. So if you look at downlink is mainly a multiplexing thing. You have to, a base station simultaneously has to serve multiple users. Okay. So for example, I mean, typical base station in LTE might serve 10 users per TTI. I'm just an example. Okay. So whatever waveform you have, you should easily be able to partition the resources. I think that is where OFDM played a very, very critical role. And one more thing in the downlink is the transmission is done by the base station. And generally base stations can be expensive compared to UAs. So base station can do advanced techniques to reduce the PAPR or CFR. Okay, so that way PAPR may not be such a big deal in the downlink. Okay, of course, I mean, it would be nice to have low PAPR so that the energy efficiency can be improved. That I agree. But it's not as much as in the uplink. So if you look at uplink, most of the times the coverage is limited by uplink because your cell phone has to transmit maximum power it can transmit is 23 dBm. And uplink is from a UA perspective, strictly from a UA perspective, uplink there's no multiplexing other than its own transmission. Okay, so that way, but still it has multiple users are going to transmit. So it's like a MAC channel, it's called multiple access channel. So in the multiple access channel, some synchronization across the users is required. Okay, so that gives you an opportunity to use a non-OFDM waveform there. Even a single carrier waveform could do, but since people want to tie it with the OFDM grid, people have been using DFT spread OFDM has used DFT spread OFDM in 4G and 5G. They moved to pure OFDM. Okay. One more thing that we have to understand in uplink is, see, this notion of PAPR, it actually depends on the PA that you use. Okay, so it's very, very much tied to the implementation. It's while there is a certain waveform PAPR, So at least what we understand is that some PAs are very, very optimized to specific modulations and other things. Okay. So PAPR does play an important role in the uplink. Okay, coverage is determined by uplink. So that is one place where maybe we might have to tweak the waveform a bit so that coverage can be satisfied. But saying that again, so when you go to higher frequencies, when you go to very high frequency like 6 gigahertz and 7 gigahertz, as I was pointing you, FWA is the main game there. In FWA, does it really matter does PAPR matter because the fixed wireless access, so power may not be such a big constraint. So you can pump out more power and still live with OFDM. That's something to think about.
Okay. Thank you, Dr. Ganti. The next question I have is for Satish from Geo, Satish Jamadagni. So I think his slides preempted some of my questions I had for him in terms of, so has OFDM met? And I also see that, you are mentioning that there's already leaning towards some of the one of the waveform. Okay. So going towards 6G, okay, what is, which you think is the key requirement? If EMBB, if you leave it alone, among the other segments or the other waveforms or the other requirement use cases, what do you think will be the key requirement which the new waveform, if we bring out a new waveform, which is the requirement that the waveform needs to service?
See, there are two terms I don't like. PAPR has been stretched, abused. It's power efficiency. That is all it is. When it comes to power efficiency, 10 years back, yeah, I mean, it could have made a lot of sense talking about PAPR. But then today, the same companies who talk of putting AI accelerators in your phone still talk of PAPR. Come on. There's a lot of complexity that can be packed into the uplink waveform. And PAPR is not a limitation today for all practical purposes. I mean, you have complex semiconductor, compound semiconductor PAs which are available. There are efficiencies in the power amplifiers also, which has been achieved over a period of time, which is substantial. So this whole debate of PAPR is nonsense. Second part, MRSS. Operators talk of MRSS. Certain parties have used MRSS to perpetuate this OFDM business. So I'm not against OFDM. If for 6G, it can bring substantial amount of spectral efficiency onto the table, perfectly fine. But then typically what happens is some vague argument of backward compatibility, which is what MRSS forces upon you. MRSS says, oh no, I need to have backward compatibility, so thou shalt not think beyond some waveform which is time and frequency in correlation with your previous generation of technology. This has become a game. So we have to look past MRSS and PAPR. These are no longer the binding factors for a waveform analysis. For some odd reason, it's still used as the yardstick. And I think we have to move beyond this. And these are the two things we will have to give away. That should answer your question in the sense that these are not parameters. You ask me what are the parameters, I'm telling you what are not the parameters. That means there are other parameters which can be used to benchmark 6G waveform and use it appropriately. Thank you.
Thank you, Satish. So the next question I have is for Dr. Vivek from GB University. So what are there are a lot of discussion on the waveforms. Okay, so what are the, waveforms you feel are the leading candidates? And maybe you can just name drop the other candidates, but pick a few of them which are the leading candidates, and how does it contrast with the existing 4G, 5G? Okay. And another question which sort of comes as we move up, we have started seeing a lot more MIMO, massive MIMO sort of discussion. And do waveform and massive MIMO, do they have any sort of correlation? Okay. Are they affect each other or they're independent of each other? So just 2-3 aspects of the waveform that you can just comment.
So am I audible?
Yes, please.
Yeah, yeah. So yeah, thank you. So when we are talking about OFDM, so OFDM worked fine with 4G and 5G systems, but now when you come to 6G systems, then you're talking about ultra high reliability, integrated sensing and communication. You want to operate in terahertz band. Now there OFDM starts to underperform. So I mean, the previous panelist did not agree with the PAPR, but I think PAPR is one of the issues here. And high Doppler shift and limited flexibilities in dispersive channels. I think these are one of the key concerns one needs to take care while designing, while choosing one of the candidate waveforms for 6G. Now, I think from my perspective, the runner would be the OTFS based waveforms, because leaving everything aside, if you want to integrate sensing into your communication, then I think OTFS is the is one of the main contenders that, because it very nicely integrates your uh, because it operates in delayed Doppler domain, so it nicely integrates your sensing capabilities. So that is one thing. I mean, there are other waveforms as well. Let's say you have AFDM, you have FBMC, you have GFDM, but all those have their own limitations. But I think OTFS would work in because it it is shown that it works well under high mobility scenarios, and it is good. Uh, it will nicely integrate sensing capabilities. And uh, and to answer your second question about how the massive MIMO thing comes into picture while designing the waveforms. So I think as you increase your number of antennas at your transmitter or receiver, you are actually unlocking uh, a, a special degrees of freedom, which would actually relax some of the constraints. So that is one thing. Uh, so while designing the waveforms, I think it will actually help you to, the waveform should be designed in such a way that you can implement it on massive MIMO. Moreover, when you're talking about communication in sub terahertz or millimeter wave, so there are some other factors that kick in, which is the phase noise and other hardware imperfections at those frequencies. So that is why wave the new waveform will just not be about the spectral efficiency, but it is also about the compatibility with the advanced antenna architectures. So I think that answers your question.
Thank you. Thanks. I think why you named one leading candidate. Let us go around the panel and find out. So the next question I have is for Mr. Mombasawala. Uh, Thank you for being on panel. So one of the thing that we have started seeing is that we started with FR1, 4G was FR1, then 5G brought in FR2. Now we are talking of FR3. FR1 is sub 6 gigahertz. FR2 is between 24 to 71 gigahertz, and FR3 is 7 to 24. So the question I have is that is it okay to expect a single waveform to perform across all these all these bands? Okay, is it feasible? Is it a good idea? What is your comments? Okay, and if there are multiple candidates, are there candidates which do better in one band versus the other band? Any comments from you?
So Prakash, thanks for having me. I mean, it is too early to predict a lot of things that you asked, but at the same time, I'll just explain you what is actually happening in the industry as we speak to a lot of people. During the recent meeting in March in Korea, 6GWS workshop, there is an overarching statement that operator has given that they only want to see 6G with two important parameters. Okay, reduce operating cost and increase the revenue. That's all you have to actually give us. uh, don't give us the story the way you gave in 5G by overselling 5G which never worked for FR2 well. Okay, I don't think there are adoption of FR2 for even fixed wireless in majority of the world. Considering the total cost of ownership, which is basically related to spectral efficiency, energy efficiency, RAN simplification, these are the parameters we have to look at reducing going forward in waveforms. And what needs to increase is basically ubiquitous coverage. That means, whether we want to integrate terrestrial and non-terrestrial network and add the sensing as an element of revenue generation. People are talking about other elements of revenue as well, which includes AI as a service, but that will take time. Okay, that will take quite a good time. So there is an agreement in the industry with CP-OFDM as the baseline waveform for 6G. Continue your search for improvement, okay, going forward, regardless of whatever we are talking as bands today. Okay, it is very unlikely that we will start venturing into different waveforms for different bands while we have not even stabilized for sub-6 or even for a centimeter band. So OFDM cannot be written off, as Professor Ganti said. It is a waveform that we also have tried in FR2 and sub-terahertz band for sensing, both in our company, both for monostatic and bistatic mode, and it pretty worked well with a good resolution for at least human identification of drones and the elements that are of concern to us. So it's not going to go away. And to answer your question, for different bands, the waveform may be same, may not be same. We do not know. The other candidates like OTFS is in the reckoning. Generalized frequency division multiplexing, filter bank multi-carrier, they are also in the reckoning. But industry fraternity says that you have to baseline on CP, OFDM and OFDM. So that performance remains kind of a benchmark, and all others have to prove better to transition onto those waveforms. I'm quite intrigued by this idea that AI-based waveform, which can actually do channel estimation, learn it, and then adjust equalizers, etc. For different conditions and different use cases would be a good idea. But what compute power, at what cost, what complexity, nobody has an answer as of now, and we'll have to wait and watch.
Thank you, Mr. Mombaswala. So that anyway nicely leads to the question I have for the next candidate, next speaker, which is Charles from NVIDIA. So the question I have is, there is a stock of AI RAN. Okay, AI for RAN, AI for networks, AI for RAN, and RAN for AI, and so on. You don't know, all forms of permutation combination with AI word and computer networks are being used. And even words like, AI native air interface, and these things are being discussed. Okay. And like I said, one level we're talking of energy efficiency, one level we're talking of AI. So what are your thoughts? What are you seeing in the industry? Is it feasible? Okay, can we prototype something? Okay, as of today. Okay, so maybe some thoughts from you.
Yeah, thanks, Prakash and Pradeep, for giving me an opportunity to talk in this panel. So I take this question in two parts. One is what is the feasibility, especially when it comes to jazzy things like dynamic waveforms and other things. That's the second part of the question that we'll answer. And the first part of the question is it AI for RAN? Is it something that is going to work? And what is the state of the art? Where are we with respect to using AI within the layer 1 or layer 2 pipeline for when it comes to RAN, right? So, I mean, as you might have seen in several forums, there have been several demonstrations of having AI-based neural network models, having running the inferencing in real time within the PUSH pipeline or the L2 stack and performing the AI-based improvements for various algorithms. And one such example is a neural network-based channel estimation model, which was demonstrated in the GTC, last GTC. So in this model, the whole training was done using a digital twin, which is equivalent to a physical world. You try to simulate the physical world in a digital twin and then train the model using ray tracing methods, and take that trained model, put it back into the real layer one, and run the inferencing. And that inferencing has to complete within that slot duration, whatever is the time budget that is available for that particular module. Right? So all these things have been proven that it can work, and the real-time constraints of 500 microseconds or even lower is possible with AI running in different computes. Be it there are demonstrations even in different platforms, whether it is FPGA or a ARM-based solution or a GPU-based solution. So different levels of complexity of the algorithms can be run on different levels of compute, and GPU is one of the computes that can help on making this as a reality, right? So what I mean is it really fully productized and industrialized? Not yet. So we still have working on frameworks to collect a huge amount of data, which are site-specific data, do the training or retraining of the model for each of the sites in a specific way, and then push that trained model back into the DU to run the inferencing for that particular site. So these are some of the things that will require a lot of development, and also work is in progress in making these work in a real-time environment and also in an industrialized manner. So forums like ARAN Alliance and ORAN are spending a lot of effort in making this as a reality. So that's the status of A for RAN, whether it can run within the RAN part of it or not. Yes, it is possible to run them in real time constrained environment. Coming to the second part of the question, so is it really possible to have a dynamic waveform, which is learning the environment and adjusting the waveforms itself? Yes, it is possible from a compute perspective and from the capacity of the different hardware available today, the state-of-the-art computation engines available, whether be it FPGA or GPU, these are all possible. But the timeline to showcase or demonstrate in a real-world scenario with such a dynamic waveform will really depend on how the 3GPP discussions on waveforms proceed, as some of the previous speakers talked about. Whether do we need something else other than OFDM itself is a question mark. So having a dynamic waveform is even further away, I would say.
Thank you. There's a lot of discussion of energy efficiency. Okay. And 5G, they said they need to improve energy efficiency. So the question I have is energy efficiency only the problem of the waveform? What are the elements? Where does, how much does the waveform affect the energy efficiency? Can we do anything with respect to the waveform and help in energy efficiency? I'm assuming energy efficiency is a larger problem of the complete system. But how much impact does a waveform have on the energy efficiency?
Thank you, Prakash. So, Prakash, I will not be able to give exact numbers because I don't know, but I can generally give you the high-level thoughts on this. See, on the base station, one of the main guzzlers is the PAs. PAs generally have low efficiency. And I now I'm frightened to use the word peer after Satish warning, but you have to do a little bit of back off. So the energy efficiency does decrease a bit because of that. So the waveform does play a role in the energy efficiency of the entire system. But saying that, of course, there's a compute that's involved in that. It depends on the number of antennas you have, number of digital chains that you are putting. So it's a complicated setup. It's not that the waveform is the only big thing here. As one of the previous speakers pointed out, it has to MIMO is going to play a role. I mean, how are you going to do your equalization is going to play a role. Everything is going to play a role for energy efficiency, including your FEC. Okay, so because, for example, if you have a lot of retransmissions, then that's also waste of energy. Yes, so that's the problem. I mean, so waveform does play a role, but there are other elements to that. On the uplink, uplink also similar observations hold true. But one thing we found out was that even in cell phones, the modem is the one which is a big guzzler of energy even now. Specifically, when you start going to the cell edge, things become a little bit problematic in terms of this thing. See, how many times you retry? For example, Pratch, how many times Pratch gets connected? So there's a huge energy guzzler. Okay. So all these things have to be taken care when you do an optimization of energy. It's just not that only waveform plays a significant role. I agree, but it's not the only thing. Okay. And one more thing I want to add is this AML thing, AML. Okay. So again, if once AML comes into picture, we have to really rethink about how energy efficient is it in terms of, you have to look at the whole data cycle again. It's just not that inference plays a role. You have to have large GPUs which do the compute of the models and other things. Okay. It's a combination of all of this. Yeah. Thank you.
Thank you. Just a follow-up question to that, Dr. Ganti. Is it that, see, somehow people are associating AI/ML will always use a GPU and it will be like NVIDIA and you require a data center. Will we not have ASICs that will come in which can do AI/ML and that will be energy efficient? Is it not a thing?
That's absolutely true. At least even now for inference, there are lots of small ASICs which can do this. I mean, much more lower profile ASICs. But I think still the data training part, none of these chips are, I mean, at least as of now, I mean, I'm not an expert on that, but I don't think there are too many things which can replace NVIDIA as of now.
Okay.
Yeah. And you have to look at the cost.
Yeah, that's true.
Yeah. Thank you.
Thank you, Dr. So do we have Dr. Kiran back? Is he audible? Dr. Kuchi, are you? No, Dr. Kuchi, I still can't hear you. Vaishali and Asif, can you see if there's anything we can do? So the bottom where you have the mic, rightmost audio. Still not audible. Okay. So meanwhile, I'll I'll ask the next question to Meek. Okay. Maybe Mr. Mombasawala can also join in the same question. So compared to, you're part of the T&M industry and there's a lot of engagement you will be seeing with a lot of R&D labs and so on. What sort of demands are you seeing with respect to the waveform? Are you seeing anything interesting, anything new? Okay. Other than what is already talked about, are you seeing more push towards something,
So I think we talked through so much things already. Now I try to illustrate also a little bit during my talks that, of course, there are a lot of requests towards OFDM-based things, variation of these, and try to get the better understanding in the technical details, how to really optimize performance for those, and all these different variants that we discussed already. Maybe what's really new is, of course, the machine learning-based approaches that also have a totally different handling of these things, as they are not really predefined anymore. That, of course, has a bigger impact in the test and measurement industry. And I guess we all have a lot of demonstrations ongoing, trying to understand what are the requirements. It starts off with really maybe simple things also to contribute to the training process using test information for data to train certain models, right? So a totally different thing that we used to do in the past. So we use physical or created signals from the instruments for training certain models, which is not a test task in that, it's a training task, if you like. So interesting new areas here around machine learning. And maybe what's also totally new, or certainly to a certain extent new, is the sensing bit in it. Because when we are in communication, we used to test things by emulating the one or the other side. You test the transmitter, you put to measure something the transmitter is doing, you put something into a receiver, so you are emulating the other side. For sensing, it's of course different, as we need to emulate or know about the objects, the characteristics of the objects, which is then a calculation process done at the device in the test, and then you compare what the object is doing. So there's also a major thing which is different, which we know about maybe more from the automotive industry, from the car. Of course, you have test strategies in this respect, but they now come in combination with the communication part, which is also new. So I would say specific to the waveform, it's not so much difference apart from the machine learning environment, but we have other aspects that come on top and that are new. And also personally, in my view, related to massive MIMO also, I mean, we've got these higher number of antenna elements coming up, specifically for the FR3 frequency ranges, and the importance of certain over-the-air measurements are, in contrast to the mostly done conducted measurements in FR1, still are maybe again getting emphasis, right? So the support from spatial multiplexing in combination with some beamforming for multiple user scenarios in the cell, that's also getting more traction.
Thank you. Mr. Mombasa,
Yeah,
you would like to?
Yeah, I just want to add what Mike said, and I take a liberty in just sharing the screen if you allow me, but it is not allowing me. So anyway, so what I'm going to talk about is what our customers are looking at in 6G. Okay, it is not just about waveform that people are talking about. It is one of those topics. We have the whole spectrum valley in which people are talking about productization of ultra massive MIMO, the channel sounding, etc. at FR3 level, channel conditioning, etc. at FI3 level, dynamic spectrum sharing, etc. What is not something that has taken shape really in the product form is new waveform. So that's where people are doing a lot of research, and also at sub terahertz. But the major push is now shifting towards the synthetic data that people are looking at for RAN capabilities. So there are three jargons which has come in, and the first one is AI RAN, where the optimization technique for RAN is the one that people are talking about. We want to have these synthetic data out of digital twinning of large scale cities, or through ray tracing of channel modeling, etc., that we want to have the RAN optimization. The other one is also AI and RAN together, AI and RAN operation together, and then AI on RAN, which is going to come maybe after a few years. So that's where is the maximum, I would say, research or the efforts that industry is putting, in addition to the NTN and ISEC use cases that people are wanting to examine. We are seeing lesser traction on 6G core and RIS for now. That's where we don't see much of the traction. So this is the current state of affair, and I believe that AI RAN with CSI compression is going to solve a lot of problems going forward.
Okay, thank you. Dr. Kuchi there? Okay, so while we try to get him on board, we're very sorry for this one. We'll talk to Satish. So Satish, I think some of them you already covered. I think with respect to waveform, there was a number given, that is, I think the target given is any new waveform should be at least 10% better than the existing one. I think that was discussed in the 3G workshop. The second thing I think the operators were talking about is, look, don't upgrade the network regularly. Don't come with 5G, 6G. We don't want any more G. Just give me SDR like upgrades. Okay. So what are what was the requirement, or what are your thoughts on this? What was the background and what is the operators even saying about this?
There was a broad statement which came out from the operators, mainly the European operators, which said they would prefer to have a software upgrade. I don't think software upgrade is practical. Forget about any waveform change. Even if you do a MIMO order upgrade, you will end up rejig. You will end up with a rejig of the hardware. So hardware rejig is inevitable, and for some odd reason, the luxury of using previous generation bandwidth is always with the Western operators, never with us, because we'll find a way to use it to the capacity, and that's always been happening. And most of the Asian operators have never asked for MRSS, for example, or any such mechanisms. It's only the European operators who. I'll just give an example. The LTE towers on an average European operator is loaded only to about 40 to 60%, whereas in India it is something around 80 to 90%. 5G is less primarily because of other issues, coverage, and your ability to stick on to the base station. But that's another issue. But that's the level of loading that we are seeing for the spectrum that we have. These are issues that will have to be taken into account. I mean, these are the practical issues that will have to be taken into account. And software upgrade not realizable. MIMO efficiency is far more important for us. Waveform, okay, can live with whatever we have, but then MIMO is what was expected to have given 5G that massive boost both in coverage and capacity. You forget about multi-user MIMO. I'm talking about single user MIMO beamforming. You can do broad beamforming, which is nothing but sectorization. But if you start narrowing the beam, you get into serious trouble, even with single user MIMO. These are very simple issues that has to be solved for practicality in an operator network. Unless we do that, how does an operator see capacity or coverage enhancement, and where is the motivation for investing in a technology which does not even give orders of magnitude enhancement over previous generation technology? No, it doesn't.
Thank you, Satish. I think that gives the R&D community a motivation to bring in, experiment and bring in value to upgrade. Otherwise, we are spending more money on just very minor incremental change. Okay. So the next question I have is for Charles. So in terms of we have to create test beds on waveform. Any suggestions? I think if people want to do waveform study, waveform experimentation, what sort of test beds are you seeing in the industry?
Okay, I mean, when it comes to testbed, especially for 6G, there are some distinct or unique requirements in 6G. So one of them is the addition of sensing on top of the communication. So it's not just a communication setup or a testbed that is good enough. So you also need to have the testbed which is capable of experimenting with sensing aspects. Second is the higher order bandwidth, so 200 megahertz and beyond. And the third additional requirement or the complexity is in the form of antenna array size. So we are talking about 128 or more antenna elements or ports per radio. So all of these requirements really add a huge complexity, and the compute requirement goes up significantly higher. So the test bed should be really capable of providing that much of compute, and also should be easy to program and easy to modify as and when required, because it's more of an exploratory space as of now, where we are comparing different waveforms, different techniques. So it's not something that is set in stone. You optimize it for it and then get away with a test bed. So in that sense, the test bed should be fully programmable. It should be fully capable of providing the horsepower that you need. So traditionally, the test beds have been based on FPGA, a large set of FPGA boards managing the layer one baseband processing, some set of software-defined radio boards, and then COT servers like x86 or any of the components. So going forward with the pace at which the research has to be completed for the waveforms and the number of waveforms that we need to compare and contrast. So it's not an easy job to develop the programs or the waveform transmitter and receiver chain using RTL in FPGA-based platforms and then trying to conduct experiments in a quicker way. So this is where generic compute platforms like GPUs or any GPP or any DPU kind of platforms can be used so that the experiments can be conducted much quicker and you do the development in a much higher language level of language for programming. For example, you can do the programming either in Python, CUDA, or C++, or any such high-level language. So this gives you a lot of flexibility for researchers to quickly try out things and experiment various things. And also, traditionally, it has been purely based on 3GPP defined channel models, which have been used for evaluating the waveforms for performance and efficiency and so on. So given the availability of digital twins, so the testbed can also embed the digital twin to make sure that you're able to test the spectral efficiency or other parameters that you're trying to evaluate with the new waveforms in a more realistic environment.
Thank you, Charles. I think a lot of my members will be keen on, creating test beds, and we should probably have a small specific discussion or a workshop only on the test bed aspects. Okay. So I don't know, is Dr. Kuchi here? Vaishali and Shweta, is he still there? I saw him leave and join. Okay. Is he on stage?
Yes, so he's joining in some minutes. Like in
Okay.
1 or 2 minutes, he's joining.
Okay. So meanwhile, I can ask Meek one question on, we've, railways, we were discussing we were doing project with railways. And one of the requirements they had is, look, I don't care too much about downlink. Can I get the asymmetry in the other way? That is, they want more uplink and less downlink. And they say, we don't have so many users. Okay, so hence it doesn't matter. I don't need a massive amount of downlink. I want to skew the downlink versus uplink. Okay, because there the security, there was CCTVs on the train, and the information they get from outside is small, and they want a lot more data to go up. Is it feasible to implement such thing? Are you seeing any action in these sort of activities?
Well, not too much, to be honest. I mean, so the weakness of the uplink, I'm also kind of hesitant to use a PR discussion or bring that up again. But obviously, we always had the weaker link in the uplink, and I think in principle, it's always good to.
Can you hear me now?
Yes, Dr. Kuchi.
Okay, thank you.
Yeah.
All right. So to improve the uplink is, of course, always a valuable goal to achieve. It's not maybe only from railways. Although acknowledge they have a certain specific conditions. What's new or what can be seen is ideas of maybe allowing a certain, or what we call a post distortion, so allowing a worse performance on the uplink chain compensated by some maybe also machine learning based receiver strategy on the base station receiver side. So you deliberately allow a worse transmission quality to the device sizes side to enable the same performance on the link by adding some computational compensation, maybe trained on the base station receiver side, and by that compensating the imbalance between uplink and downlink. It's also an interesting idea to a certain extent because capabilities on the uplink side are always kind of restricted. So this is in this respect a little bit a new approach we are seeing coming up here and there.
Thank you, Dr. Meek. So, Dr. Kuchi, thanks for your patience. Thanks for joining. Can you hear me now?
Yeah.
Yeah. So there's one question I was asking, that is, what is your specific issues of OFDM, and can we not tweak it? Okay, that is what I was asking you. So
Yeah. I'll take that question. Um, you know, there was a paper that talked about the information capacity achieving property of OFDM that Radhakrishna talked about. And the same also is true for single carrier systems. Of course, there are some if and buts in both cases. Both are capacity achieving waveforms. Of course, the kind of single carrier we use in OFDM is different. Apart from that, let's talk about the base station. Generally, you add up many signals, if not multiple users, whether they are time frequency multiplexed. But for creating beams, you will have to add up many signals in different directions, transmit them in different directions. That's what base stations do, what we call massive MIMO or MIMO. By the way, the same happens in the satellite. It also has 32 beams or 64 beams. So on board the satellite and on the base station, it's the same technology. You create beams. So when you create beams, unless you want to create one beam and serve one user, you will have to add up signals. When you add up many signals, then the PA has to be dimensioned, with that peak and average swing. So downlink is always like that. Now let's come back to OFDM. The actually since 2008, almost all the things that we ever want to accomplish, it could be accomplished using I wouldn't call it OFDM, using what is called subcarriers. Okay, so you have OFDM, and then you want to reduce PAPR, you have a DFT module put in the front, then you have lower PAPR, then you spectrally shape it, but still in the end it's a OFDM signal from the system, designing the system point of view. You have a narrowband IoT, had a single tone. I mean, practically any waveform that we know of, that we developed in the last so many years, you can approximate it to some degree by tweaking here and there and represent it as an OFDM signal. Okay, from that perspective, OFDM based waveforms, the sentence that the study items agreed upon, is actually practically allows you to do many things. While of course, if you have some pet waveform that cannot be, you don't want to represent it in terms of subcarriers, then you're out of luck. Okay, so OFDM framework, what I call, allows you to synthesize almost any waveform that you love in some one way or the other. That's exactly what we did with this new name we have had, OFDM, and we put a T in the middle. Actually, it is OFDM signal, and at the same time, it is a Nyquist class of signals, that is TDMA signal. It is actually TDMA and OFDM at the same time. And it solves other problems. You may call it Doppler or PAPR, whatever it is. So in a nutshell, OFDM can be used to serve the needs, whether it is latency, whether it is capacity, whether it is MIMO or PAPR. So, well, when it comes to the challenges of not achieving so much MIMO gain or coverage, these are all engineering problems we have to solve, but keep the subcarrier framework. So I hope that sort of answers the question.
Prakash, you are not audible.
Thank you. So what you're saying is the big chunk going through is not there anymore. Everything is sliced and diced, and after that you can do whatever you want. Okay, some things are mandatory, then or it's not going to change for the next few years and so on. So now that, sorry, we couldn't have you earlier, so maybe I'll ask you a follow-up question because you missed the first round. So why is waveform discussions in SDO so contentious? Why is there so much hullabaloo and so much heat around the waveform? I assume
See,
SDOs are always heated, but waveform seems to be a very touchy topic. What is the, if you can briefly...
it is very touchy for the right reasons, because the hardware that you build is going to be very sensitive to the kind of waveform you put in. Waveform includes 2-3 different things. The let's say modulation is part of the waveform, the 64 QAM, 256 QAM. That the constellation points you put in are very critical, and the PA and LNA, the mixer, all these things, is a different art, and there is a cost to it, there is a price to it, there is a power consumption to it. And so when you touch the waveform, everybody is very touchy about it, because you have ACLR, EVM, those are the holy grail issues as far as the RF performance is concerned. So it's for the right reasons. People are very, very conscious about waveform. Of course, MIMO is a layer on top of it, and MIMO is, I wouldn't see it as a separate thing. Actually, MIMO and waveform are one and the same in some sense. They're physical layer, and MIMO also deals with power amplifiers, antennas, and mixers. So they go hand in hand. But one thing I want to say though, in uplink, still, when we do the 5G testing in our own base stations, most phones actually transmit a single layer for whatever reason. Although, and that's it, single layer most phones transmit. But in practice, I think the best you can do is only 2 with horizontal and vertical polarizations. So in the uplink, I don't foresee, it's mostly for physical reasons. That is basically the wireless channel propagation. It's hard to push more than 2 layers in an outdoor environment. In Wi-Fi, maybe it's different. There are a lot of reflections. On the downlink, actually, there's no limit on how many beams you can create. I mean, 3 sectors is basically a third order MIMO, and then you start splitting the sector into subsectors. So that is the basic way to view MIMO and beams. So if you start doing that, you'll start seeing the gain. I mean, there are many ways to do it, but I think splitting the 360 degrees into subsector is what gives you the maximum bang for the buck.
Thank you, Dr. Pichai. So I think there's a set of questions people are asking questions here. So we have one question for Dr. Vivek, one for Dr. Radha, and then we will go to the audience questions. Dr. Vivek, what is your thoughts on ISAC, joint sensing and so on? You think, is it something which we should get excited about? There's work happening on waveforms, because sensing seems to be something different compared to communications.
Yeah. Thank you for the question. Yes, I think ISAC, because IMT 2030 has also elaborated ISAC. So I think there is a merit to ISAC, because I mean, ISAC could be a game changer in terms of positioning and localization. So because when we are talking about centimeter level accuracy for even passive objects, be it with device or device free objects, then I think ISAC would come into picture. Moreover, there are certain, I mean, other uh, other aspects that ISAC looks upon, where uh, you want to share the waveform as well as the hardware in terms of ISAC. So I think ISAC is a good starting point, and we should get excited about it. And all the waveforms, I think, be it any version of OFDM or OTFS, they are, I think, the central idea around uh, behind building those waveforms is they also want to incorporate sensing within the waveforms. So I think people are actually, preparing for bringing in sensing into the communication aspect.
Okay,
Thanks.
thank you. So maybe we'll look at the audience questions. We have a set of people asking questions. So one is, there's a question to Professor Ganti from IIT Kharagpur, Survas Shekhar. So comparison curve of OFDM versus OTFS shows OFDM is superior. Okay. So can it be explained again? So Dr. Ganti.
Prakash, I actually answered that to him.
Okay.
The markers were not very clear. Actually, OTFS gives a little bit slight. I mean, both of them are very similar. Okay? There's a slight gap. That's all.
Okay.
Yeah.
And then there's a question by Abhijit is not mentioned, so I think the panel anybody can pick it up. Why should we make DFT OFDM for DL? Okay. In general, UL makes sense due to power constraint. Why in DL? So I'm not sure who is addressed to.
Prakash, I can take that question.
Yes, please.
Yeah. So, like I mentioned before, if you are going to create beams, then whatever is the waveform, they all look like OFDM to the power amplifier. Okay. On the other hand, if you want to build a system with large coverage, and you don't intend to create, let's say coverage is your goal, largest possible coverage you can achieve, and not worry about multiplexing many users over beams and increase the bits per second per hertz, then the right thing to do would be basically use the PA to the fullest possible extent and drive it. But whether this is how it would be done, that's questionable, because then whether the PA, once it is designed for OFDM, it's difficult to get more out of it. We have seen it in 5G because the PA manufacturers have dimensioned it a certain lifetime. Getting more power out of it is always difficult. So these decisions have to be made 5-6 years in advance, whether there is such a requirement that you want to have the longest possible reach and beamform it. It's like sort of like a backhaul. I'll leave it at that.
Okay, thank you. So there's another question saying, is there going to be a refarming of existing FDD bands towards TDD? I think what they are asking is, right now, any band you should either operate in FDD or in TDD. Can it be, is it fruitful to look at, take the FDD, run TDD so that maybe you can do uplink, downlink percentage split change?
Prakash, can I do first go on this question?
Yes, please.
Yeah. So, okay, again, a controversial thing. So, TED is good.
I like controversy. Otherwise, panel will get boring. Please.
The TED is good. And 5G made a lot of noise about TED. They have like one whole section in 3GPP dedicated to TED, multiple formats, there are 140 formats of TED. But if you now look globally, everyone uses only one format. Yes. There's a very specific reason for that, but because of interference and other things. So previously, one other person asked, how do you improve uplink capacity? Now there's nothing dynamic in nature; it's fixed. It's a big issue. I don't think. Why should we move from FDD to TDD? At least in the lower bands, I don't see any specific reason, except there's a little bit loss in spectrum. But at least FDD gives you an opportunity to have better uplink, at least in terms of capacity. Maybe Satish and others can give a different view.
So anybody else wants to respond on that?
Yeah, I also think that this, of course, in theoretical terms, you can certainly reuse FDD bands and operate TDD and these FDD downlink uplink bands. But also for practical reasons, I think it would really hard to be doing this, because that has to happen at a certain day. And there are deployments where you have certain devices around operating in these frequency bands, and then switching that scheme. You essentially need to make sure every device under operation understands that new situation, right? And there will be interference scenarios if you mix that up. So there's no practical way in doing this. And option, as said before, I think there's also no motivation to do it actually. So why should that happen? My view.
Okay. So another question,
So I just wanted to highlight one issue called ducting that gets pretty serious, and that is something that has to be solved. It's primarily interference coming far away.
Satish? We just lost your audio for a few seconds.
It is called as ducting. It
Okay.
affects LED systems, primarily synchronized across geography. This is interference from faraway base stations. And in order to increase capacity, it's interference, essentially interference, capacity. And this is substantial in certain regions. And this is something that is typically ignored, not talked about much, but that comes in the way of capacity. And this is also something that has to be solved in TDD systems, because as we go forward, it's only going to be higher frequencies. So it's a very critical issue that has to be solved in FDD systems. It affects your capacity and coverage. It's something to be solved in TDD systems.
Thank you. So there's one more question. The context of 6G, where AI run, NOMA, and Isaac are expected to work in unison, what are the fundamental limitations, trade-off that must be addressed to achieve seamless integration? How do we design a unified framework? I mean, it's a large question, but I think what they are saying is AI, NOMA, and Isaac, is it possible to put them together? So it's an open question. Anybody wants to pick it up? Okay, so I don't see Dr. Kuchi, you want to?
Can you hear me?
Yes, yes.
So see, we have to live in a practical world. That is, we have fundamental requirements to be met in terms of transitioning from 5G to 6G. There's already so much pain in non-monetizing. So this puts some limits, as you saw in the study item framework. So in fact, the study item framework for 6G says that the system should function without AI, without any, without, AI is not mandatory. So what this means is that there are features here and there, but fundamentally the system is designed without AI, and AI is something you use either proprietarily or maybe in some special cases here and there. So that's the story about AI as far as it goes into the system. NOMA, I'm not so sure, because I think this has been around for like almost 10 years. It's got stuck somewhere, so it's not moving ahead. Sensing is, it's a complicated subject. I think that's why it's moved into second phase of 6G development. First phase is not going to include the sensing. So whatever we have in 5G advanced, if you want to do sensing, use it. Sensing will be looked at later on. By the way, you can do sensing without at least you can do sensing without actually having any standard in place also. Right? So there are some advantages having a standard and signaling, but sensing is not something you need to even define, strictly speaking. So these are very plain layman views. Thank you.
Thank you. So in fact, I had seen some, I don't know, paper or this one video on where you could use Wi-Fi to detect people. Okay. So they're worried about Wi-Fi can be used to spy. So I don't know, that seems close to sensing. So maybe we'll start closing. I wanted, what you say now, maybe a generic question to all of you saying, the Indian R&D community who want to do work on, waveforms and develop expertise and develop contributions. What is the thoughts and suggestion? How do we grow the community? How do we do a lot more engagement or discussion on this? Second, as a standby question or whatever is it possible to have an open model or open design of a waveform? Right now we have somebody pushing and proposing a waveform, but is it possible to have a generic waveform or an open waveform which get discussed across on common test beds? Okay, so open question to all of you. Any of you can say the Indian, or if not in the 6G, if 6G window is already getting shorter, going towards 6G, enhancing 6G, 6G advanced, and towards 7G. What needs to be done in the Indian R&D community?
Prakash,
Yes.
I'll take a go at the first question.
Okay.
So it is essentially what I'm saying, what as like Kiran pointed out, see, OFDM is just a framework. It just gives you time and frequency resources. Theoretically, it does not restrict what you put inside that. Yes, so I think people should develop a lot more waveforms, put them inside that. Even I think OTFS is also can be put as a part of the OFDM framework. I mean, that's what I mean. At least I understand. So I think that is something we should do. I mean, there are a lot more fundamental questions that has to be answered. See, 5G, all said and done, a lot of promises were unkept. Okay, so I think that is the first thing that we should focus on. Make sure that you get more spectral efficiency, massive MIMO works, NB-IoT works. I think that is what is going to be the first phase of 6G. I think we should be, we should be realistic in that, and then other things are going to come into picture. Okay. Regarding the second thing, open thing, I really don't know how it's going to work out with all these patents and other issues. It would be nice to do that, but I really don't know. I mean, I was thinking about this question, but I'm not sure on how to get it working.
Anybody else wants to take what Indian R&D? How do we bring in more R&D on waveforms, more contributions?
So there is a practical issue that will have to be taken into account. One is, especially when you talk of 3GPP, it's consensus driven. So obviously there are certain baselines that have already come out, and things work within the scope of certain limitations. MRSS being one of the limitation I told you, the backward compatibility push or pressure. But apart from all this, one of the biggest learning in 5G is that 5G has not necessarily succeeded even in the vertical space. Both in terms of the waveforms, intrinsic waveforms of the verticals, and also the architecture. I can just give you an example. For example, V2X, your definition of what a base station is varies very differently from what your EMBB base station definition is. It has to be a roadside unit, and it has to communicate with multiple of these vehicles, which will also have small entities, device or whatever you might call it. So this is where the biggest opportunity for India is, and this is something that the research community should focus on, and this is precisely where we can bring in much of the differentiation. And if you want to compete in the larger space, you been to one of the RAN1 meeting rooms? You'll be lost just in the meeting room. Forget about contributing. You need to have so much of weight and background work that you will have to do. I suspect most of the Indian entities are still not there. I'm not trying to discourage. I mean, there can always be a different story, but this is a realistic scenario. This is very important that people have to. And this whole dream of universal open air interface and all this stuff. See, this is not today's story. This has been going on forever. It never gets realized. 2000, I was part of an organization which was called a software defined radio. And the only channel that they wanted to define, the only standard that they wanted to have was what was called as a universal control channel, UCCS. That's the end of story. Every phone will have something called as universal control channel. You sync, you get some basic data formats are defined. From there, you can start asking for whatever radio personality you want. It's a long story. Anyway, that's not going anywhere. I mean, practically, those days are gone, unless and until again we have another cycle of neural nets, and it's a few years away from practical realization. But this is where we stand. If somebody, small Indian communities want to define new waveforms, it's for the verticals. That's where the opportunity space exists, and it is open. Thank you.
Thank you, Satish.
Prakash, can I ask one question?
Yes, please.
The panelists here. To panelists, I mean, Kiran, Satish, everyone. Yeah.
Please, please.
Should we look at an Indian waveform? Should we look at an Indian spec for some of the verticals at least? Is it something that we should think about?
Most definitely. If you look at the 5G waveform, 5G, whatever definition of base station plus waveform plus whatever system is defined, and use that for fixed wireless. No, I mean, you'll have to strip down a lot of things which are defined. 3GPP specifications are primarily for mobility. Even if you want to adopt that for fixed wireless, it's a costly proposition. I'm talking of economics here. If somebody wants to use a 5G base station for fixed wireless, which has all the mobility components which you paid for but never use, it's orders of scale magnitude much higher, not practical. So trust me, even in millimeter wave or fixed wireless, you'll start seeing certain technologies which are very very cost effective. I don't want to give too much of, I don't want to get into the details, but then it's something that you can look forward to. Cost effective solution. The reason I'm talking about this is, you take 5G. We've talked about this separately as well, Radha. So the opportunity lies where, if you can strip down, have a very cost effective base station today for 5G, strip it down just for fixed wireless, and make it cost effective, both on the UE side, on the base station side. We are in business.
Okay.
We are in business.
Yeah, as you
Just an
said,
example.
fixed wireless access, both sides, you can have control. Yeah, you're right, absolutely right. Yeah.
Thank you. Anybody else? Dr. Kuchi, you wanted to say something?
Yeah, see, the way to have your own contributions fructify into an industrialized product is not to go to 3GPP and say we'll have this thing, that thing of our own. That won't work. It's a globally harmonized standard, and it's a different play. But India is large enough market to do other things. What Satish has mentioned, there are many other things actually that can be discussed, where you don't need the complexity of a 3GPP spec. It just bogs you down to implement so many things which are not even required. So you have to really build a lean spec from the scratch that you can develop quickly, and also adopt it for some local use cases, that without disturbing the larger ecosystem. It's quite possible. So it's indeed possible.
Okay, thank you. I think we're quite, we're just, I think, a few minutes beyond the time given. So my takeaway is that, it is possible maybe, but if you have to go and convince everybody in 3GPP to accept it, maybe that is the difficult portion. Maybe pick up a leaner and a simpler profile and a small industry segment where you don't need the whole stack. In fact, I was telling somebody or talking while discussing that 3GPP these days started looking like the IBM, the mainframe, where only 2, 3 companies can make IBM, only IBM could make mainframe. So maybe there's a scope for when something gets big, it tends to, big, so big that it disintegrates at the edges. Okay, so maybe we look at the edges. I don't know, is it narrowband IoT? Is it IoT? Is it satellite? Or is it, underwater communications or whatever? Okay. So thank you. I would have loved to go on because such a large panel of experts. So thanks, Dr. Meek Kotkamp from Roden Schwartz, Mr. Charles Santosham from NVIDIA, Professor Radhakrishna Ganti from IIT Madras, Dr. Vivek Chowdhury from Gautam Buddha University, Mr. Mohammad Saeed Mombasawala from Keysight, Mr. Satish Jamadagni from Geo, and Professor Kiran Kuchi from YC. So thank you all. Kindly, if you would use a slide, send it to us, and if you can also send a lot of comments you made, if you can just WhatsApp it to me or send an email. I need to create a summary of this. It will help me do the summary. Okay. So thank you, and I'll give the floor to Pradeep.
Okay, great. Yes, very interesting session. Thanks, Prakash, for moderating. I think we had great experts and panelists who gave their opinions. We had 3 rounds of good presentations also, giving us an overall view. Definitely the concluding remarks, I would have made some notes if I want to just run through it quickly. Mr. Make was very clear that, he gave clearly certain sources as well to refer to from, how T-Mobile is looking, where FR3 is not so potential wave, spectrum for them, and proposed waveforms from their perspective, because they're also giving you the unbiased opinion, because they look for what customers, being a DNM, looking for what customers ask for. So from that, the proposals were definitely coming on as an FDSS in uplink for lower PAPR, It can be OTFDM, ZAC OTFS, or CPOFDM. But definitely with the shaping, the TTFS with shaping, where OFDM along with the shaping was adding a lot of value. I could see some graphs given where they were able to bring down the certain aspects, right? Giving giving it as an optional for uplink and downlink both. At the same time, they were also acknowledging for specific use cases. The waveforms that can also cater for specific use cases can be for zero edge, for a zero energy wastage or energy efficient, waveforms. Or it can be something very specific to NTN or hyper latency, right? And ISAC and OTF. For ISAC, they're recommending OTFS. They also cover, Mike also covered a few things on how to test, showing beautifully how those spectrum analyzers were helping conclude certain remarks, right? So that was from, and then from the second presentation, we had a beautiful topic that is covering right from the history of the OFDM, as dating back to 1910 to more than 100 years of history, was covered by Dr. Ganti. Give us a lot of brief into it. How this, finally the OFDM, what happened from 2000 onwards, what are the strengths of it, what are the weaknesses of it, right? But still, how OFDM can still stay back, right? Because he made a very concluding remark that OFDM has life still, right? It is there for to stay back for another 10 years because the results, the test and experiments have shown up to 500 kilometers per hour speed also. OFDM is performing on par with OTFS and other candidate waveforms. So definitely that also gives us an pointer that like OFDM is there to stay, and it need not necessarily that it is outdated and we have to move to a new waveform. But at the same time, there were some contrasting views which also showed that there is a need for further study also. So definitely the topic of dilemma and potential new waveforms still holds good. And also he gave us one good slides on how these parameters, what are parameters which need to look for, right? It can be from in terms of scalability, it can in terms of reliability, in terms of integration with MIMO robustness, right? And what kind of solutions do we need to have some, but there's one very common slides across, which are also, very concurring with all the experts, panelists, and speakers, that do we need to have a, do we need to still consider just one waveform across spectrums or across technologies, and why not have a use case specific waveforms and bring everything under an umbrella called 6G? So that also can bring a more, a realistic approach, and the targets can be met, because we also need to look for integration of NTN, ISAC, IoT, industrial IoT. So in one cases where we was also agreed that like there is no need of a heavy waveforms as such. So it was a very good this thing. But and then we had one more presentation from Satish, which is covering a lot of practical aspects of how do we move forward, right? So he also brought in some KPIs aspects, 6G waveforms and the associated KPIs, where there was a low PAPR budget, targets with a 140 dB budget, right? For 400 megahertz. These KPIs are actually very realistic, and those are need to be looked into for further studies, right? And he also brought in a topic that in REN plenary there is a uh, hard written that OFDM candidates needs to be pursued for further benchmarking and listing. So that is one thing, at least in the study phase, we need to still consider OFDM, right? And massive MIMO. So major concluding remarks from Satish presentation we got was, how do we know we need to focus on fixing MIMO issues, right? The squinting issues, waveform studies, right? Which also need to adapt to uh, the waveform squinting, the MIMO issues and everything. And I also add the capacity issues as we go ahead of the order of MIMO orders. So it is not about because right now massive MIMO is perfectly working for a smaller band, even up to 100 megahertz. But in future, in 6G, if we speak about 400 megahertz bandwidth, so these may come into lot of aspects. So that also needs to be did. So it's not about just OFDM. It's not about just OTFS. It's also about fixing many other things, which also gives us the edge to meet our further targets. So that was one of the a good concluding remarks from the third keynote by Mr. Satish. And thanks to Prakash, we had a wonderful panel discussion. Lots of intriguing questions will come in. It's like, why do we need different waveforms? Why do we need, are, any specific parameters that needs to be considered? Are there any some very clear comments that came were like PAPR and MRSS are highly over exaggerated, right? So spectral efficiency is something need to be looked into it. Charles gave us very clear ideas on the AI and how the neural networks has been used for channel estimation, how they are being trained now. The data models are trained in the digital twin and brought back. Yes, there are operational issues that needs to be dealt in the future, but definitely a lot of work going on. But maybe it's too early to get into the operations and get into live practical fields, but a lot of work is also going on in that area. How computing requirements are needed for the test beds going forward, because we are talking about a really higher order MIMOs, higher antenna elements. And finally, there are good arguments on, do we need to have an Indian specific waveform or standardization in India itself, which are specific to our market needs, because I know we have a very large market to cater for. How we can strip down a lot of things to for cater for FW use cases to make it more cost efficient. So I think there are a lot of good topics that came up, good questions that came up. Overall, we had a good session, I would say, and I'm extremely grateful and for the TSDSA to hosting such sessions, and Tech Deep Dive conference was, I believe, was very fruitful, very intriguing for me also. I hope all the participants also enjoyed it. Thanks to all the speakers, panelists who gave us their very interesting viewpoints for us to dwell further. And whether the dilemma exists, yes, I believe so far we can say still the dilemma exists. There definitely OFDM is there to stay further, but there are a lot of things to fix around OFDM, and at the same time we can also look positively for new waveforms as well. So the study must go on. Hopefully everyone enjoy the session. If there are any questions, there also can be posted. If there is a feedback that can be put forward in the link given in the slide. Link given in the
Yes,
slide.
so there's an announcement from my side.
Yeah, please.
Yeah. So there is a gentle reminder to all attendees or participants to share your feedback using the following, which is displaying on the screen, and I have put it into the chat box already. Your input helps us to improve future sessions. Thank you once again for your active participation. We hope you found the sessions of PTD 2025 engaging and insightful. Thank you so much, everyone.
Thank you all.
Thank you.
Have a great
everybody. Have a great evening.
Thank you.
Thank you.
Thank you.
Bye.
Bye bye. Thank you.
Bye-bye.